Our next speaker is Vincent. And the next one, Lucas. You can prepare yourself. Lucas.
Is he online?
No, he's here. No, sorry.
Yes.
Please, you can start.
Okay, so hi everyone. I'm a PhD student in applied mathematics, and I'm here to talk about joint work about interpretable flow-based models. So as you may know, normalizing flows consists in transforming a simple base distribution into the target through a series of smooth invertible transformations. And the main question is, which transformations should be chosen? Toth and his co-authors noticed that Hamiltonian transformations are good candidates since they are invertible and symplectic, making their Jacobian determinant exactly equal to 1, which is computationally efficient. So their neural Hamiltonian flows architecture, or NHF, is made of 4 neural networks black boxes, 2 within an encoder for generating momenta and simulate Hamiltonian dynamics, and 2 to parameterize the kinetic and potential energies of the system. They claim that their model should be highly interpretable since it's physics-based, and so in their mind, the potential energy should learn the modes of data, for example. But we found that it was not always the case, so our solution consists in enforcing even more physics and fixing the quadratic, the kinetic term to be quadratic, as in classical mechanics. And now when targeting a multimodal distribution, the fixed kinetic version, second row here, always learned a multimodal potential, while it's not always the case with the usual NHF, first row here, and a problem in the middle. In the latter case, we found that the multimodality was instead transferred to the momenta. We highlighted that fixed kinetic models, with or without an encoder, in fact, are very robust to the choice of hyperparameters. For example, models trained on 10 leapfrog steps are still performing with the 5 or 40, which is not always the case with usual NHF. And we also tested our models on image generation and showed that the fixed kinetic version behaves similarly to its usual version. And finally, we adapted the Boltzmann generators framework to NHF in order to use them for Bayesian inference. And the idea is to transform the Bayesian prior into the posterior with NHF. We tested it on inferring cosmological parameters from supernovae observations. As you can see, our models are able to recover approximation of the means and standard deviations of omega m and h. For exactness, of course, you'd have to consider other types of algorithms, such as MCMC methods, keeping in mind that there's always a trade-off between the quality of sampling and the computational cost. So please talk to me if you have questions, and thanks a lot.
Thanks, Vincent.